Okay, let's see. Okay, we'll see how long this all lasts. I gotta get the, anyway, welcome back. So we are now getting into lesson 4. We've gone through 1 through 3. You should see that I believe they're all 1, 2, and 3 are just extended till October 20th, which is when the midterm is, so you can continue to work on them, go back to them. This one will have a due date of next week to encourage you to finish or get started and get going on it. So we have our weekly schedule here. It's kind of, and so we finished off 3. I haven't gotten those. We're doing lesson 4 today. We should get mostly through it. If not, we'll pick up a few last things. On Monday, I did go over that last little thing on even and odd functions, but I wasn't able to record because I had worse things going on than today. I'm recording today, so if you still have questions about even or odd functions, after we get through this, we could take a quick peek at it. It's just a little bit. Okay. And hopefully we maintain connections all the way through. What I also did is I previewed the practice test. Yeah, we'll see how this all works. Okay, that's better. And so I've incorporated some of the questions from the practice test directly into the PowerPoint, so we won't necessarily go into the practice test because we're doing it as we go through the information. See how that, okay, we're doing good. So, first off, we're going to talk about inverse functions. And we got a lot of, sorry, let me go back. I need, oh. Okay, I need to use this one. Okay, I apologize. There we go. Okay, so the main thing, we're talking about inverse functions. We've got to get used to the notation. We use this little -1, which f to the -1 looks like an exponent, but it's not. It's just it's a symbol that's telling us we have the inverse function. So think of the minus as maybe an opposite. So the function that will undo the other function. Down here, they're emphasizing it's not a -1 exponent, which when you have a -1 exponent, it's just the reciprocal. That's not what we're talking about. We're talking about an inverse function. Okay, and what happens in an inverse function is, so like this one down here is what we might call the forward function. It sends 2 to 4, and so the corresponding, what an inverse function will do is it really just switches the input and output. So for this particular one, we know that the inverse function would take 4 as an input, and the output would be good. And it would take also, since this other point is here, it would take 12 as an input, and the output would be 5. So that's the idea of an inverse function. We have experience with each of us some different ways. So, yes.
So if it looks like an f to the -1, so if you had a function to the -1, how do you know if it's to the -1st power or if it's supposed to be an inverse? If it kind of looks
They typically won't use that on a function, an exponent. If they were to, what they would do is this. And then that's clearly to the -1 power.
Okay.
When they put it on the inside, it's kind of like attached to that name of the function. But that's a good question, yeah. And typically they would do something like this if they were going to square it or something. You put parentheses saying we're doing it to the whole function. But mathematicians are not known for their high level of consistency. So let's see. Now the weird thing is I went to the next slide and this is not going to the next slide. So, oh there, okay, it's just slow. Just okay. So just think in general what an inverse function is. If this is the function, or if this is the operation, which is, what's that guy doing? Or you're digging a hole. So what would be the inverse? Fill it back in. Okay, so in life we have all of these things. We're writing a paper and we delete a paragraph. Oops, I want that paragraph back. What do? Undo. Good. And we didn't, when they first came out with word processors, we didn't have the undo function. But it's nice to have that because all the time, right? And sometimes you can even, they've got computers that doesn't really delete it, it puts it in the trash, so you can take it out of the trash, right? So being able to undo something is very important. And in math, the same thing happens. With math, remember, a function takes an input and somehow assigns it to an output. So the input goes to an output. The inverse is just the reverse process. So what you're going to see in these inverses when we start talking about it, if the function has an addition, what are you going to see in the inverse?
Subtraction.
Good. So we'll say this is just the function, and this is the inverse. If we have multiplication in the function, you'll see division. If you have a square in the function, you'll see a square root. So, those are all the operations we've been working with that undo things. That's what we're going to do. However, sometimes they just talk about a function. So here we're given some inverse function of h is sending 6 to 2. So what would be the corresponding input and output values of the original function? Very good. You would plug in 2 and you would get 6 as your answer. So again, so part of this is just, if we have a table of values, it's just reading things backwards on the graph and such. So we'll kind of go through this. And some of it's not really difficult, and there's no calculation to do. It's just switch them. So we'll see how this all works, and then we'll also talk about linear equations as we go forward. Okay, so first of all, what we're talking about is there a test? If we had two functions, is there a way to tell if the two functions are inverses of each other? And there's sort of the steps here, which I'm not going to read through it, but I'll talk through it. Let me ask you this. So we have a function f and a function g. In the function f, where do we start? Everything starts with the input, right? So we start at x, we do something to it, we get it at y. So what would the inverse function, if it is an inverse, what would it do with y?
Flip the sign. Make it a negative.
So
Put it right back where it got it from, right? It would put it right back to x. Okay.
the x would be divided by -3, and it would subtract from it?
You're on the right track. Yeah, so and the thing is when you do things in reverse, not only are the operations reversed, but they're done in the opposite order. Okay, so let's think through this. Here we're multiplying by -3, adding 5 in that order. So we should subtract 5 and then divide by -3, which seems to be what, so this is a pretty good candidate. The way we can test it is if we take, let me change coloring here. Let's make G blue, like I did down there. If we take the composition of the function, so we're going to do f of g of x. If we do this composition, we're plugging in g of x to f of x. And so we actually plug x into g, get that answer, and then that gets plugged into f. So we should end up, if they're true inverses, we did something and then we undid it, we should end back up at x, right? Just x. And it should work both ways. So let's see if this happens. So the composition of f, g getting into f, so what we do is we take the f function, minus 3x, and I put a big open parentheses because that's where g is going to go, plus 5. And what we're doing is we're plugging the function g of x, which happens to be x minus 5 over -3. And now we're going to simplify this, and if we end up with x, then that's a good candidate. We haven't proved it yet. We have to do both ways, but if it doesn't work, then we're done. So -3 divided by -3, we can cancel those out, right? And we're left with x minus 5 plus 5, minus 5 plus 5, 0. This equals x. Bless you. So we haven't proved it yet, but we've proved half of it, that, yeah, when you plug g into f, you get back to x. So it's undoing. It's working as an inverse. The other thing, to fully prove it, you would have to do it the other way around. Let's see if I've got enough room. G of f of x. And so the g function is x minus 5, so that's x minus 5 over 3. And then in there, that's where we plug in the f function, -3x plus 5. If you take off those parentheses, right, we could do that because there's nothing outside, you get a plus 5 minus 5. So we're getting g of f of x. These are going to become 0. You get minus 3x. Oops, this should be minus 3 down here, over minus 3. -3 divided by -3, apologize. That's why I like to have both. Now it's hard for you guys to see over here, especially the low ones. Negative 3 divided by negative 3 is 1. So this is equal to x. We just verified that they are inverses. But we also, by looking at it, it sort of seemed that that would be it, right? So you not only see the opposite operations, you also see them done in the opposite order. Just like, if you take an engine apart, the reverse operations to put it back together, but when you put it back together, you got to start with the pieces in the middle, right? And you work out. When you take it apart, you start from the outside and work in. So that's what an inverse. So this, again, that's what all of this is saying. If we do a composition of functions between the two, both in both directions, both orders, we'll get x. If we get anything other than x, it's not an inverse. What if we got the answer negative x?
Well, it's not that.
It's not x. Good, good. It's negative x. So it's not back where we started. It's the opposite of where we started, right? So good. We have to get just x. Okay. So there's some of the homework in there. And again, you could go through a few of these. We would do compositions of functions with these two, and you can see we're cubing the x and then subtracting 4. Over here you're adding 4 and then taking the cube root, which are inverses. So it seems like it could be, but we'd go through that process. I want to verifying. This one's a little more simple, so let's just take a quick look. So what we do is we do f of g of x. See if this works. F of x is x to the 5th. So take everything to the 5th power. G of x is 1/5 x. And then when we go to simplify, what happens? Well, we get this 1/5 it's basically this times itself 5 times, right? You get 1/5 to the 5th power. You get x to the 5th power. We don't get x, okay? It's not x. We don't really have to find what it is. We just know it's not going to be x. So this is not. What they're doing here is if this had been x, if g had been x to the 1/5 power, you would see that is an inverse, taken to the 5th, but 1/5 times x is not an inverse. So these are not inverses. And we don't have to check the other one, because if this one doesn't work, it's not going to be an inverse. There's a few functions out there that are sort of an inverse one way, but then they don't work the other way. But they're very rare. And you might stumble across them. People look for them for like when they're doing tests, because you'll test it and it's equal to x. You say, yes, it is. But then there's, again, just a very few that are not. Okay, so we've got that so far with inverses. That, again, inverse gets us back to where we started. We dig the hole and then we undig it. We fill it back in. I thought I got some, so here's another verification. We'll go through that. And then finding the domain and range. And again, I won't read through all of this. This is here for you in case you want to go back and read. So let's talk about the function f of x. Its domain will become what for the inverse function of x? Well, let's back up a step. What is the domain of the function f of x? Potential. What variable are we focusing on when we talk about the domain? The input, the x, all x's, which could be negative infinity to infinity. But it's what the thing we want to say is it's the x values. What is the range of any function? All the y values. So since we're switching the y values and the x values by the inverse, right? That's what the inverse does. Wouldn't it make sense that the domain of the first function is what the range of the second of the inverse function would be, because we switched x and y, And the range of the first function is going to give you the domain of the inverse function, because you just switched x and the y. So good. That's where it comes from, is it really literally is just switching the x and the y. So the domain and range switch places. So if you know the domain of the first function, you know the range of the inverse function. If you know the range of the first function, you know the domain of the inverse function. This is nice because when we have these two functions, oftentimes it's the domain that's a little easier to find. So you just find the domain of each, and then that way you can swap them and get the range for each. Okay. But one of the things that's needed for a function to have a true inverse, because remember, what is the rule that allows a relationship to be a function? Each input can have how many outputs? Only one. So notice, remember, like with x squared, a cubic, while say this will go here, this could be y equals 2. The value of y equals 2 could actually have two different inputs that created it. So when you go backwards, this is no longer a function, is it? So what we're going to see is, like with a quadratic, we're going to have to sort of ignore half of the function. We're going to have to sort of delete this part, and what you'll see is the inverse function is the square root function, which graphs something like this. It's like a parabola on its side, but it's only half of it. Okay, so this is what's called a one-to-one function. Each input has only one output. Each output has only one input.
So that's why square root functions look so weird.
Yes. Yeah, it's really just it's a parabola on its side, but it's only half of the parabola. And because, when you're taking the square root of something, it's really just becomes y equals square root of x. But there's actually always, if you want to fully get it, you'd do y equals negative the square root of x, and you'd get a full parabola. But you have to graph it as two separate functions, because the calculators come to recognize this idea of functions. So to keep it a function, the inverse, to truly have an inverse, the original function has to be one-to-one. Each input has only one output. If it's not, we restrict the domain. We sort of cut off the part that's causing us problems. Okay, and you'll see with some of these functions, and we'll go through that. Again, we won't spend too much time, but here we go. We're given the domain of some function. We're not told what the function is, but we're told the domain is 1 to infinity. We're told that the range is negative 2 to 2. So what would be, talking about the inverse function, what would be the domain of the inverse function? The range. And the range is negative infinity to 2. Good. And then, thank you. And then the range of the inverse function's going to be the domain, right? So they just switch places. Okay, that's all we're going to do. You're going to have some problems where you're given a table and you're asked to find f of 60. Now this is what I would call the forward function, right? It's not the inverse. How do I look up f of 60? I go to where the input's 60 and I get its output. So this one would be equal to 50. How do I do now? This negative 1's down here, but this is the how would I look up the inverse function of 60?
Just go to the y's.
Excellent. It's the same thing, but in the reverse direction. We go to the y's and we find the x that goes with it. So this one, the inverse function of 60, y is 60, x is 70. Okay, so it's a reverse lookup. So literally, you just do things backwards. That so far so good? Okay. I'll look over here because this thing rocks make sure everyone's doing okay. If we've got a graph, again, this is the same type of concept. Using the graph figure A, find the inverse function of g at 1. So where do we look up this 1? What is this 1? Is it an x or a y? It is a y. So I'm going to do this in green. So I'm looking, here's the y value of 1. It hit the graph right here. It has an x value of 3. So we would say that equals 3. So it's just looking it up that direction. What if we want the inverse function at 4? Again, same thing. We go to the y value of 4. And there's the x value. It looks like it's about 5.5. About as good as we can get. So instead of going to the x and finding the y, we're going to the y and finding the x. Just reverse. Okay, so just think reverse order. And again, some of the homework problems will give you a graph and ask you to do that. But again, if you don't know what to do, you're kind of just stuck. How do I do this? But it's just a reverse lookup. Okay. Now we're going to get into how do we find an inverse. And again, what does an inverse do with the x and the y's? It switches them. So what we're going to do with this is we will, instead of f of x, just to make it easier, we'll call this y equals 1/3 x minus 5. So that is our function. The steps to go is, let's just make the inverse function. Let's just switch x and y. So everywhere we see a y, we put an x. Everywhere we see an x, we put a, you got it, a y. That is the inverse function, but it's not quite, usually we're used to functions having y equals. So then the next step is to solve for y. So we will add 5 to both sides. And so you kind of see how you get the inverse, how the inverse is going to be the opposite operations, because we swapped it and then we got to move everything over to the other side. We have to do the opposite things in the opposite order, right? So this becomes x plus 5 equals 1/3 y, and 1/3 y, not x. And then we multiply both sides by 3. And I'm going to emphasize multiply both sides by 3. 3 divided by 3 is 1. We end up with y equals 3x plus 5. And we can kind of see it. So we're adding 5 first and then multiplying by 3 instead of dividing by 3. So this is its inverse. And the way we write an inverse function, we use the notation f inverse of x equals 3 times x plus 5. Now, yes, you could take that 3 and distribute it and have 3x plus 15, but I think if you don't do that, you see that you can see the inverse relationship a lot easier. If you distribute it through, it's harder to see. So my suggestion is go ahead and leave it as it is. But that's how we can find an inverse. We just rewrite it, swap the x and the y, and solve for y, and we've got our inverse. Easy to say, but sometimes hard to do. Okay, because there'll be a couple examples, and let's see what they give us. So like with this one, it might be a little complicated, but again, we just y equals x to the third minus 2. First step is to switch the x and the y. X equals y to the third minus 2. In a sense, we have the inverse function, right? And there's a lot of graphing tools like Desmos. I could graph this and it would produce its graph. So there's more and more. Part of it is the technology and sort of the feeling of we want to write this as f inverse, so we still have to solve for y. So we'll do that step. What do we do first? Add the 2 to both sides. Good. And so we get x plus 2 equals y to the third. And then what do we do? Cube root, right. You could think of it, remember the cube root is to the 1/3 power. So if you take 3 times 1/3, that's to the first power. You could write it either way. But if you want, you could write it this way. This is the cube root. So I'll do this up here. You could either use cube root or the 1/3 power. Okay. We take the cube root of both sides. The cube root of something cubed is just going to be y. And then this is now the cube root of x plus 2. And again, we use inverse notation, so we say this is f inverse of x. We're going to replace the y is equal to the cube root of x plus 2. Remember that little 3 there. And again, we see things being done in the reverse order and the reverse. So instead of subtracting 2, we're adding 2, and we're doing that first. And then we're taking the cube root up here, we cube it, and then subtract 2. So reverse order, reverse operations. Okay. Another thing that happens with inverse functions is, let me go here, is there's this line here. Let me actually, let me draw it with a line. Does anyone know what the equation of that line would be? It's the good. We talked about the identity line. It's so it's the line y equals x. Along that point, each x value is the same as the y value, and so forth, right? And so if you switch them, you've got 1, 1, and you switch it, and then you have 1, 1. Can you tell the difference? No. So this is the line along which, when you do an inverse, if there's a point along here, it's not going to change. But when you go to graph an inverse, what's going to happen is each of these points. So this is 2, right? 2, 1. It will now become 1, 2, right? The x and y's are going to change. This point, which is 1, 0, is going to become 0, 1. So it's going to go there. Let's see if I can find another good point. Here's 2. See, I don't know quite what that is. A little bit above 0 and negative 2. So a little, let's see, I go to negative 2 and a little bit above to kind of help me. And so I could connect these something like that. Now my drawing's not so great, and that's okay. We're not going to have you do too much, but you could see it would be a reflection over that line, right? Because x and y's are all changing. So that's another way graphically you can tell an inverse, because they will be symmetric. They will be a reflection over the line y equals x. Yes?
So with the parabola and then the
Square root.
function, why does it like kind of stop at the x-axis then?
See if I can do
This one
that.
is like all over the...
Right. So what we do with the square root function, or say x squared, is we only consider, we first turn it to a 1-to-1 function, which would be here. And we've got this line y equals x. Let's see if I could draw that line very good. Not really. Well, it's something like that. Part of it's on one side, part of it's on the other. And so when you get the square root function, it reflects over and crosses. So there's this one point, you get 1, 1, right? If you take 1 and you square it, you get 1. Take the square root of 1, you get 1. So there's this point where they will cross, but at every other point will be a switching the x and the y. So it kind of goes like this. And actually, if I get rid of this line, I don't know if I can't quite get rid of that line, so I will move it. I will delete it. So the line would kind of go like through there, and it's a reflection over that line. Okay. Sometimes if you go into a graphing tool, which we will use, it will do it much nicer. So we could do f of x equals x squared, and we see it looks like that. See, I think I can restrict the domain. Let's see how I forget the syntax. Maybe it is that. Oh. I think I have to go like. Does that do it? There we go. So there's a way with decimals to say just graph the part that's greater than or equal to 0 for x squared. So you can restrict the domain. Took me about half hour of looking through videos to figure it out, and then I keep forgetting it. And then we could also say g of x, which is its inverse, is the square root. Where is our square root function? Oh, there it is. Square root of x. Let's change colors just to... And then if we put in the line y equals x, make it green and we'll dash it. It looks, that's what you would see, is this sort of reflection over that line. Yes?
So I'm still confused as to why when you have like the parabola, that one's only half of it.
Because if we had the full parabola over here, the inverse function would be this full one, would be a parabola on its side, but that's not a function, right? Because it would violate the vertical line test. And so it's, what's so important about functions? Well, it's just the way they want to see math. So they want everything to be a function in our mathematics until there's other, you get into higher level math where things don't have to be a function. But because it was about 20 years ago, they decided everything, functions will unify the teaching of math. So we have to do this. Before we could talk about a parabola that's on its side and has both sides, has both basically the positive square root. And, yeah, it just wouldn't be a function. But again, we could decide to set up our mathematics that relations are just as good to work with, and we could do that. But because they want to have this function as a unifying thing, it's not a function. It violates the function rule. So
you could draw the whole sideways.
Right. In fact,
We just don't.
yeah, and most of our tools, because they set it up that way, to draw that part, you would have to say y equals negative square root of x, and we could get it, but it has to be two pieces.
Okay.
But that's what it would truly look like. And so if you don't restrict the domain, so you could think in those terms, but the new function is not a, well, it's not a function. The new inverse is not a function. Does that make sense?
Yeah.
Okay, so that's, it's kind of a technicality, but an important one. Okay. Let's see, we're 10, 11, 15. So now we're into linear functions. So we talked about inverses. We're going to talk a little bit about linear functions, which may be fairly familiar to you. What is a linear function? It's a function that when we graph it, ends up being a line. Okay, so let's just talk about what are the qualities of a line. Does a line have any thickness? Not real. Technically it doesn't. We have to have some thickness to see it, but a thick line and a thin line are just that. There's our drawing of it. So the idea is that every line is just a collection of points, so they're all the same thickness. That's not any difference. Is there any curvature to a line? No. So they're all straight. So that means there's really only two properties that a line has. One property is sort of what makes lines different is how steep they are, right? So the red line is steeper than the green line. My axes are kind of off kilter a little bit, but you get the idea that, so there's a steepness to each of the lines, and we call that slope. So that is a characteristic. If it's going up, then the slope is positive. If it's going downward, then we have a negative slope. This one has a positive slope. And what we'll talk about is how to calculate that slope and what it is. The only other characteristic is sort of the height. One line could be, like, they could have the same slope. I could draw parallel lines, which we'll talk about in a little bit later. Parallel lines, and then their slopes are the same, right? Their steepness is the same, but what's different about them is sort of how high they are, and we can measure that anywhere, but we choose to measure it where it crosses the y-axis. So the other thing we look at is, I'll call it starting value, which is its y-intercept. So that y-intercept. So there's just two things that make it different, and what we're going to see is it's reflected in the equation of a line. We'll get that y as an output is equal to the slope times x. The slope is a measure of how things are changing, so that's why it's a multiplication thing. And then the y-intercept is where we start. Notice if you put in 0 for x, this goes away and you just have the y-intercept. So that's sort of where y is starting. And you might remember this formula gets written as y equals mx, m times x, plus b. Or if we were to write it in the sort of the correct order, remember this all comes from Arabic, the Arabs would have read it b plus mx is the order. Sometimes you'll see it as y equals b plus mx. So because b is a start where you're going to start on the y-axis, and m is going to give you your change. So again, and addition is commutative, so we could write them in either order. It's okay. But that's linear equations. Okay, so here's some more formalized ways of doing it. We can represent the linear equation again with the sort of form of y equals mx plus b. We can say f of x equals mx plus b using function notation. We can represent it as a table of values, 0, 1, 2, 3, and then you'll see that the change between the y is constant because the slope is always the same along the line because there's no curvature. We can also show it as a graph. Okay, and if you're going to have an arrow on one end, you really should have the arrow on the other end because that's the other side of a line. There are not short lines and long lines, they're all infinite, is the concept we work with, is that every line goes on infinitely in both directions. Okay, but sometimes, okay, we're talking about some situation that has a starting value, and we look at
like a piecewise function, are those not lines because they stop?
They're line segments. So sometimes we do talk about line segments if we've got a piecewise function. When we're talking linear equations, though, the concept is they don't stop in either way. Now, yes, we can restrict the domain and say, hey, negative values don't make sense, so we're going to go from 0 this way. So we could talk, and we give that official name of array. So this one, if we didn't put this, we could call it a ray. But if we're going to call it a line, we've got to give it that way.
Okay.
And if a piecewise, sometimes we just use line segments. Okay, so there's kind of those technicalities.
They're all just called different things.
Yeah,
But if it stops.
yes. If we just use the word line, we should be going in both directions. Okay. So again, what we see is the y-intercept will always have an x value of 0 and then some y value. That means we're on the y-axis. And we typically write this in what's called slope-intercept form, y equals mx plus b. And what I'm going to show you next is, so we can write an equation. This one I'll do, and they won't get to 2 points. So we have 2 parts to the linear equation. Okay, we have input and output, but again, the 2 characteristics is we have how it's changing, which is multiplication, and we have where it starts, which is the thing that's either added or subtraction. So as we look through this, and a lot of times I won't read a full question, I will look, okay, here's a number. She has $20 at noon. A barista knows she has $20 in her tip jar. So that's at a particular time, right? If she makes an average of 50 cents from each customer, 50 cents from each customer, so if I had 2 customers, I'd multiply by 50 cents and I'd have $1, right? This is, so part of it when you read these, you have to see what's being multiplied and what happens at one time. How much will she have in her tip jar if she serves in more customers during her shift? So noon was when it started, right? So that's a starting. Will that ever change? No, because it's right. So the $20 she started with is our y-intercept. That's going to be our plus 20. The other one is our slope. It's our rate of change. It's how the money's coming in. She's getting 50 cents for each customer. And that's our linear equation. And again, if we put it in terms of x and y, it's really y equals 0.5x plus 20. We were going to put it in a graphing calculator. But you'll read those, some stories will give you those 2 things, a starting value and a slope, a rate of change, how things are happening per customer. Does that make sense so far? Okay. And we sort of talked about this at the beginning, but if it goes from left to right and it's going up, that's what's called an increasing, and that will tell you that the slope is positive. M is greater than 0. We'll just say that's a positive slope. If it's decreasing, then the slope is less than 0 or negative slope. And that goes with this one. This goes with that one. And if the slope is 0, so you actually, if the slope is 0, you really just have y equals b. We're going to see this with horizontal lines. There is no x in there because you multiplied it by 0, and that gives you a constant function, which is a horizontal line. So notice whatever the y-intercept is, that's the y value all the way along there. So those are the 3 things that generally happen with the line. Now we didn't talk about a vertical line, and why didn't we talk about a vertical line? Will a vertical line pass the vertical line test? No, because it's every 1 point. So it's not a function. Sometimes we will talk about it, and we'll see, a couple slides down, we'll see that its equation is x equals some number. Let's say this is 5. That's a vertical line. They're helpful for us, but they're not functions, so we don't directly talk about them too much. Okay, your TI calculator can't graph them. Desmos can handle it. Some of the newer stuff can handle it, but the TI-84 cannot graph a vertical line. Okay. So now we're going to start talking about slope. Again, this is sort of an introductory page. It has a lot of verbiage. I'm not going to read through it, but I'm going to walk you through the steps here. But this formula, y2 minus y1 over x2 minus x1, it comes from the fact that we need, if we have 2 points, there's only one line you can connect with those 2 points because there's no curvature, right? The line is straight. So you can only connect one line. So if you've got 2 points, and we just call it x1 and y1, right? Those are the first coordinates of the first point, and the second point would be x2 and y2. That we've got this formula. If we subtract the y's, we're finding out how much we're changing vertically. We subtract the x's, we're finding how much we're changing horizontally. And if we take the ratio change of the y's over the change in the x, which is what this is saying, then that's what we call slope. This little triangle is actually, it's a Greek letter. It's delta. And we even use the word delta to signify change. So in science anyway, the delta represents change. So the change of the y divided by the change in the x gives us our slope. So we're going to look at a couple ways we can do this. We could use the formula to find the slope. So finding the slope of a linear function, we just want to find the slope. I'm going to show you a way that does the same thing. But if you're slightly dyslexic or you have problems with the formula, this might help you. It's helped me a lot. What you do is you rewrite the points on one on top of the other. And you could put them in any order, it doesn't matter. And just recognize that the first coordinate is the x, the second is the y. Now that we've got them lined up, is we subtract. So take the top minus the bottom. 4 minus 9 gives us negative 5. Negative 1 minus 2 gives us what?
1.
Negative 3. Good. Because we got more negatives. This is a little hard because you have to kind of visually see that that negative went there. So we get negative 3. But notice the first one is the x, the second is the y. So what they did, and this comes from ancient India, they called this vertically. Notice we're vertically subtracting them. And then we do something crosswise. We take the x and tuck it underneath the y. And so our slope is negative 3 over negative 5, which is 3/5. Okay. What I'm going to also show you is that we'll get the same answer if we use this formula, y2 minus y1 over x2 minus x1, but it's just a little harder. So what's y2? y2, if we take this as a second point, that's 2. The first point is negative 1, so we take 2 minus negative 1 in the top. And then we have to get the x's, the correct x's in the bottom. Since 2 was our y2, 9 must be our y1. And our x1 would be 4. So notice how this is where I typically will make some kind of mistake because you got to get everything in the right place. And it's easy to get off one of them and then you got a negative slope when you should have a positive slope or something. 2 subtract negative 1, so in this case we end up with positive 3, right? 9 minus 4, 5, so we ended up with positive 3/5 right away. So some people ask, is the order important? If I would have changed which was y2 and y1, as long as I change x2 and x1, we would have gotten the same down here. We would have got negative 3 over negative 5, which in the end becomes 3/5. Okay, so 2 methods. You use whichever one is most comfortable to you. So if you're used to using the slope formula and it works well for you, go ahead and keep using it. If not, I like this one because I don't really have to remember it. I just sort of, and there's a lot of things in math that you can do this vertically and crosswise thing with. So it's more visual and it doesn't have to have a formula. And I make a lot less mistakes when I use it. So, but it takes a little bit of practice, but notice it really is doing the same thing. You're subtracting the x's, you're subtracting the y's, and then you're tucking the x underneath. When I use the formula, sometimes I put the x's in the tops and the y's in the bottom because it's, it's just, but this way it's a lot easier. I always remember the first one gets tucked underneath. So however you want to do it. Here's finding population change, and they want us to compute the rate of growth of the population. So the slope is a rate. It's how things are growing over time in this case. So we've got a year and an amount of people, a year and an amount of people. What you'll see a lot of times that's done in math is when we have years, those are the input values, the x values. 1960 is a pretty big x value, right? It's almost 2000. So a lot of times what they'll do is they'll take the first one and they'll call that 0, year 0, starting year. And then the next one is how many years since that. So 1960 to 1989, if you subtract them, is that 29 years. And so then you can get your 2 points, 275,900. And this would be 0, 287,500. And again, we could do the same thing where we line them up, and maybe this time we could put the larger number on top, and that might make the subtraction easier for us. And that's the nice thing we can do, is we can do it in any order we want, and as long as we're consistent, we will get the right values. So 29 minus 0 is 29. Right, we're going to subtract them. Ooh, they lost people, so 275 minus 287 is actually going to be a negative number. And that's what? 10,000, 11,400, something like that, maybe. Maybe I better have someone use their calculator because sometimes I get these wrong. So 275, negative
11,600.
600. Okay, I went the wrong way. And then again, to find the slope, we take the x value, tuck it underneath the y value. So we can take negative 11,600 divided by 29, and we could leave it that way, right? It's a slope, but sometimes
Negative 400.
Negative 400. So that means our population on average was losing 400 people a year. Does that make sense? So that gives some meaning to what slope is. Slope is a rate of change.
Maybe what's going on in that city that
Yeah. Poor government. They're not keeping their streets clean. I don't know. They're being mean to the people. So they said, we'll just leave. Yeah, usually if you respect people and you do some good things, people want to come live there, right? That's where you get population growth. But sometimes it's not their fault. Who knows? Okay. I just wanted this one. Maybe we'll do this one with the slope formula. Sometimes they don't give it directly to us in the right order, so they tell us about the increase here and then the years here. And sometimes 2009, you could make it year 0, but then, whatever you want to do. But again, you've got time and you've got an amount. So 2009 was the beginning. It was 1,442, small town. And then 2012, a few years later, 1,868. So we can see it's growing. And again, we could use the formula y2 minus y1 over x2 minus x1. 1868 minus 1442 divided by 2012 minus 2009. And again, you could have made one of those years 0 if you wanted, but it just depends on where you want to make the calculations. So we would subtract these, and what do we get? $1868 minus 1442, 426. And 12 from 9, or 9 from 12 is 3. Did I get that right? Yeah. And 426 divided by 3 is 142. And so that's a growth of people per year. Okay, so multiple ways to come up with those. Any questions? Doing okay? Okay. What if they give us a graph? How do we write the linear equation? Well, we know we're going to have y equals mx plus b. So looking at the graph, what's part of the equation that might pop out right away? Y equals, so we can see the y-intercept there. So that's the point 0, 3. And remember, b is going to be our 3. So we know we've got y equals mx plus 3. And what else? 1, 1 is a point on here. So what is slope? Slope is the change of the y over the change of the x. So we can visually see the y is changing by, it's going down by 2. The x is changing by 1 to get to this point. Rise over run, or dropping over run. So we can see that the slope must be -2 over 1, which we could just write as -2. Okay, so that's our slope. So we can get going from one point to another, and that's the important point. We could have chose any point, and we'd come up with the same thing. We could have chose this point up here. It went up 2, but then back 1, so it's 2 and -1. You'll see you'll get the same slope. So our equation is y equals -2x plus 3. Okay. So we can just pick off the y-intercept, find the slope by going, how much do I have to rise to get to the next point, how much do I have to run to get to the next point. That gives me my rise over run. So far, so good? Okay. We'll keep going. Let's see if we can set this one up. So another thing I like to do sometimes is I will read things backwards, and what I mean is I will start at the end, the last sentence. I'll read that first. Find a linear relationship in the form y equals n plus b that gives the yield when n stalks are planted. So again, I don't know too much about the story yet, but I know I'm looking for a linear equation. So I'm going to write that down. And again, they're using n for the variable instead of x, which is kind of cumbersome, but we're okay. Then I start looking, okay, and n is the number of stalks. So what are we talking about? Bean stalks. So I just kind of scan and I pick that out. N is bean stalks. We're told that the farmer, she plants 30 stalks, and then she gets a plant that yields 30 ounces. Each one will give 30 ounces of beans. When she plants 34 stalks, the production goes down, right? So what do we have here when they give us 30 stalks and 30 ounces, 34 stalks and 28 ounces?
We have X and Y.
We have an X and Y.
Can you just do Y2 minus Y1 and get the same answer?
You got it. You got it. So we've got our 2 points. We've got 30, and they're telling us the bean stalks are the N, or the X in this case. So the number of ounces becomes the Y, and sometimes that's the hard thing to determine. So 30 stalks gives 30 ounces, and 34 stalks, because you have more, I guess you're using up your nutrients, only gives 28 ounces of production. And again, to get the slope, we could do the y2 minus y1. So 28 minus 30, that's the y's. The x's are going to be 34 minus 30. And so it looks like we're going to get negative 2 over 4, which is negative 1/2. So it looks like in each beanstalk we produce, we reduce the output by 1/2 ounce.
I feel this farmer is wasting her time.
Yes. But she's made an...
Be looking at like what fertilizer she's using instead.
Exactly. Just use some more fertilizer and you'll be fine. So we have our slope y equals negative 1/2 N plus B. How are we going to find B now? Because how do we find the starting value? We could use something called the point slope formula, but it's an extra thing to remember. What I like to do is, what do we have here? We've got a y value and a n value, or x is what I like. We can choose one of these points, and it doesn't matter which one we do. Maybe 30-30 is a good point to choose because it's hard to mess up, right? If I plug in 30 for n, it means the result will be 30 for y, so these will be taken care of, and I'll be able to solve for b. So this is the way I go about it. So I've got 1/2 times 30, which is going to give us negative 15. Add 15 to both sides. And we get that B equals 45. So our equation becomes y equals negative 1/2 n plus 45. Which is totally meaningless, right? Because this is saying if you don't plant any beanstalks, then they'll get 45 ounces worth of production. But how can you produce anything if you... Yeah, some of these are contrived equations to torment math students. But does that make sense? What I'm going to show you is a way to save time then. And this is going to help us on something that's called regression and modeling. Is if we have our 2 points, there's a way we can use our graphing calculator. And most of you have a TI-84. You have a Casio. We'd have to look up how to do this, but it's a similar type function. It might actually even be easier. But let me pull up my TI calculator, TI-84. Points are 30-30 and 34-28. I'll show you how to do this. Okay. I'm sure somewhere along the line something's going to blow up between running all these apps. Let's see. Okay, there we go. Yeah, maybe not. What we're going to do is called regression, linear regression. It is actually a statistics function. So we go to the stat key. So I'm just going to hit the stat key. What we have to do is we have to enter in our points, and then we're going to calculate the function. So we'll start with edit. And so we just, as soon as we come in here, it's number 1, we hit enter. You should see a L1 and an L2. That's your list 1, your list 2. That's your X and your Y. Okay, so we're going to enter in 30 for the X. I'll hit it. Oops, that's 30, 30. Try that again. And then 34 for the second X, because when you hit enter, it just goes down. And then I arrow over and I'll put in the Y. So the first coordinate was 30 for the Y, and then 28 for the second Y. So notice this is kind of like the Indian way where you've got the points side by side, one above the other. So we've told it what points we have. What we have to do is then we go back to the stat function. And this time we're going to go over to calc. And what we have to do is we want linear regression, which is number 4. Now notice they also have a linear regression on number 8, which is a plus bx. You could use either one, but just make sure what they've done is they've switched ax plus b is probably the one you want. We're going to hit enter. And then notice it gives us the X list is L1, Y list is L2. We just hit enter to accept those. We don't have to do any of these, and then we get down to calculate, and it gives us the linear equation right there. So we did it. It's y equals negative 0.5 or negative 1/2 x plus 45. Okay, so this is what's called linear regression, and you can get your equations that way, any 2 points. We're going to use this a little bit later with processes that may not be exactly linear. We'll enter all the data, do the regression, and we'll get the best fitting line. And that's usually what they'll do with research, because when you do research, you collect data and it doesn't all fit a line. It might follow a line, but it might not all be exactly on the line. Okay. How many are feeling fairly comfortable with finding the equation of a line? Sort of. Maybe with some practice. Okay. I think we're just about there. And again, you're going to get some multiple chances to do it. So if they give us a table of values and they're telling us it's linear, we want to find that linear equation. How would we go about getting that linear equation? What do you notice about what could we use from this table?
Any point you want, right?
Right. And how many points do we need?
2.
2. What would be maybe one of the best points to choose?
Probably first and second.
Very good. Certainly the first. Why is this one so good to choose?
0.
Because of the 0. It's actually the y-intercept, right? It's actually, this is our value for b. If we use it, it's going to make our lives much easier. And then we could use the next one to find the slope. And that's what, so they gave us the y-intercept. So I'm just going to write it down. Y equals mx plus 12.5, because they gave us that. Now we could use the next one to find what the slope is, what the m is, and we're done. So again, you would subtract the y's. 13.5 minus 12.5. And in the bottom, we've got 2 minus 0. So it looks like we get 1 over 2. And so our equation would simply be y equals 1/2 x plus 12.5. Just like that. Now, if they didn't give us the y-intercept, we would take the two of the points they gave us, and then we'd have to go figure out what the y-intercept is by plugging in what are the points. Okay. Also, if we wanted to, we could take these 2 points and plug it in our regression, and it would give it to us as well. And sometimes that's good practice, you know, because it's a little cumbersome to do the regression. You can get there. What if they gave us the equation and asked us to make a graph of it? How would...
The y-intercept is -2, just go like down 1/4 from there.
Okay, and then we can use the slope. It's negative, so you could do the negative either way you want. Down 1/4. This is the hardest part, though, so remember the top is up and down, the bottom is left and right. If you get that backwards, you'll end up in a different place. So we'll go down 1 and then run a 4. 1, 2, 3, 4. So we got our second point. -1, +4, and then we've got 2 points. What can we do with those 2 points? Just draw a line. Yeah, so sometimes that's well, I'll go from here to here. I can draw it that way, and then I could draw it this way. There we go. Perfect. Perfect. Okay. What if they give us the equation, and then we're asked to find x-intercepts? What is the property of an x-intercept? Let's come back here. This would have an x-intercept about here. Let's go up here. What would the coordinates of this x-intercept be? Looks like maybe about -7, 0. So what we see with every x-intercept, the y value equals 0. Okay, so when they ask us to find an x-intercept, we simply set y equal to 0, and then we're going to have to solve for x. So it's a little easier. The y-intercept is always just hanging out there. It's -4. The x-intercepts we got to work for. So we add 4 to both sides. And then we multiply, in this case, both sides by 4. 4 divided by 4 is 1. 4 times 4 is 16. And so we get an x-intercept of 16, 0. And again, you could graph this and you would see on your graphing calculator an x-intercept at 16. X equals 16, y would be 0. Okay, so just remember that with y-intercepts, that means x is 0, so you plug in 0, you got it. X-intercepts, y is 0, plug in 0 for y, and then solve. This is what we alluded to earlier. Horizontal lines are always y equals a number, because notice each point along here, the x values are different, but the y is always 3. And vertical lines are always x equals a number, because x is always the same, y is changing. So this is y equals -3. Again, a vertical line is not a function, so we typically don't use it, but it comes up as helpful sometimes. Okay, you'll see horizontal lines. And horizontal lines, these have a slope of 0. What about vertical lines? What is their slope?
Undefined.
Okay, good. Because it would be division by 0, right? Because since x is not changing, so we just call it undefined. If you were to define it, it would be an infinite slope because it's going straight up. But so it's actually it's the quickest change. It's going straight up. But and sometimes that helps to think of it as infinity, because then that helps differentiate between the vertical line and the horizontal line. Horizontal line has no change. Vertical line is all change. We're getting down to the last two concepts. Parallel lines, those are lines that don't intersect, and so they have to have the same slope for that to happen, right? So that's what you want to notice is parallel lines, the slopes are the same. Okay, so we're going to do some problems where they'll give us one line and they'll say find an equation of a line that's parallel to it. Whenever you've got parallel, you know that the two slopes are equal. That's what you know, and then you use that. If you're told that two lines are perpendicular, that means they will meet at a right angle. So when they cross each other, that's a 90-degree angle. Those are kind of important lines at times. The only way that can happen is the rise and run switch places. So if you know the slope, there's kind of two ways. If you know the slope of one of them, the other slope is going to be the negative reciprocal. Okay, so what I like to do, opposite, yeah. So if one has a slope of say 3/5, we'll call that slope 1. What is the slope of the other one? Negative 5/3. So the negative reciprocal, and it kind of makes, they've got to go in the opposite direction, so that's why one's positive, one's negative, and the rise and run switch places to make it 90 degrees. So again, what we do is we use the first line they give us to get the slope, and then we use the point that they give us. So what I did is, this is where I took a few examples directly from the online test. So you'll see these. Give the equation of the line passing through the point -4, -21, that is parallel to this line y equals 4x minus 2. So from the first line, what do we take? Since we know they're parallel, we know that the slopes will be the same. So all we know right now is that we have a slope of 4, and we're going through this point -4, -21. So we know that our new line is going to be y equals 4x plus some y-intercept. We don't, this y-intercept doesn't tell us anything. It just tells us the intercept of that line. But we now have a point, we have an x and a y value, so we can plug those in. Y is -21 when x is -4. And then we can find our b. Okay, 4 times 4 is 16. So that's -16, -21. Add 16 to both sides. And that will give us that -21 plus 16 is going to give us -5. So the equation of the line we're looking for is y equals 4x minus 5. Okay, so that was again directly out of the practice test. The test will have a similar type question. The numbers will change and such. But whenever we want parallel, we just take that slope, use it, and plug in the point. Okay. If we want perpendicular, we sort of do the same thing, except we don't take the same slope, right? This slope is 3/4, so what is our slope going to be? The opposite and the reciprocal. Good. -4/3. That's our slope. And again, we ignore, I always try to cross out that y-intercept, because sometimes people want to, oh, there's the y-intercept. But that's for some other line. We want the y-intercept of the line that's perpendicular to it, so then we've got to use this point. Y equals -4/3 x plus b. we plug in negative, or we plug in 6 for x, and we plug in negative 16 for y. And then we simplify, but it's kind of a mess, isn't it? Because you got these fractions. But 3 goes into 6, so that's not too bad. 3 goes into 6 2 times. So 4 times 2 is negative 8. And then we add 8 to both sides, right?
Why'd you do the inverse in the beginning?
Because we were told that the lines are perpendicular.
That's horizontal.
Yeah, right. When they're parallel, you take the same slope, but notice perpendicular, one line's going this way, the other line has to have the other slope. They have, so if one slope's positive, the other has to be negative, and vice versa. That's why the negative. And it just so happens, if you look at these, it's not always obvious, but it always happens to be at 90 degrees, the rise and run have to switch places. So that's the reason for the reciprocal. But good question. So negative 8 is our y-intercept. And so our equation, y equals, did I get everything right? Yeah, negative 4/3 x minus 8. Okay, and you could graph both of these lines with your graphing calculator, and you'd see they're perpendicular. Now, you might have to get your window to be a square to get it to actually look perpendicular sometimes, because the windows, it doesn't look perpendicular, but it is. And that's perpendicular. So that's the main thing. And again, you'll practice this a few times. Just remember, with perpendicular, the opposite slope and the reciprocal slope. Opposite reciprocal. Parallel, they're exactly the same. And in both cases, you need that point that they give you, you plug that in. Okay. Here's one I wanted to get at, because here's a line that's y equals negative 9. What is its slope?
It would just be on the
It's
far
just 0, right? It's just
0. This is a horizontal line, right? Is y equals is going to be, so that's always, these are our special lines, and sometimes it causes the most problems, because it's, what is that? Y equals negative 9, that's a line down here. That's 0 slope. So it's easy to confuse the two. So this line, so if I'm parallel to a horizontal line, what is the only other line that's parallel to a horizontal line? Another horizontal line. And since the horizontal line is y equals, what's the y going to be equal to?
2.
Y equals 2. Okay. Now you could, if you wanted to, you could say, okay, it's got a slope of 0, so that's y equals 0x plus b. We could plug in the x and the y, so 2 equals 0 times negative 3 plus b. Well, that's 0. Oh, b equals 2. The slope is 0. Oh, y equals 2. So you could go with the y equals mx plus b setup. But sometimes if you recognize that it's a horizontal line, oh, it's parallel, it's going to just be whatever that is. What if they wanted the perpendicular to y equals negative 2? What if we change this? What kind of line is perpendicular?
a vertical line.
Good. So it would be a perpendicular would be a vertical. And vertical has an equation of what? X equals negative 3. So again, if you think through it, it's not so bad, but you have to conceptualize, okay, vertical lines are always x equals, horizontal lines are always y equals. And that takes some practice and getting used to. So I threw that one in there. And then again, we could go through, sometimes they say a line passes through these points, so they don't give us the equation of the line. We'd have to use it to find the slope, and then we get a slope. We got a point here. We would take the negative reciprocal of the slope. Okay, so And this is the last one, linear regression. All I'm going to do is highlight that what we did previously with the graphing calculator, we will do with this one. But what we have to do is we have to enter all these points. Okay, so let me see if I can pull up the calculator at the same time. We'll go with that. We're going to keep all this stuff. So just let me show you, again, depending upon which calculator you have, things will operate a little differently. We go to Stat. We're going to go to Edit. A quick way to clean things up or to get rid of these previous dots is to arrow up, and when you're at Y2, if you'll hit Clear and then Enter, notice those are all gone. Do the same thing, go to L1, do Clear and Enter. All those points are gone. And then now you can start entering in each of the points that they give you. It's a little tedious, but you've got to get them in right, because garbage in, garbage out, right? If you make some mistakes here, you're not going to be able to get the right. And so I'm just going to put in a few of them, but you do need to put all of them in. So I'll do the first three. This isn't going to give us the correct answer, but it'll walk you through the steps once you get to the homework. So you put in all the points. 0.6. And oops, that was negative. It's supposed to be negative. And we're almost there, but I do want this recorded because I'm going to show you a few tricks. Negative 3.6. Let me just do one more point. 64.9 and 26. Okay, and again, you would, I'm almost there. Why not put them all in? Oops, that's not 26 there though. Let's clear that. Should delete it. 26 is over here. Okay. You'll hit Stat again. You'll go over to Calc, and you're going to go down to number 4. And that will give you the equation of the line. Again, this is not the correct answer because I still have 4 more points to put in. But I want to show you what's actually going on here. I want to store this equation, so I'm going to go to the vars key, which is the variable key. I'll go to vars, I'll go to yvars, and function. Wait a minute. Let's try this one more time. Okay, so we do this. Okay, I think I know what to do next. We're going to go to y equals. If I want to put that regression equation in there, that's where I go to vars. I go down to statistics because that's what I've been doing. And I want equations. And I want the regression equation. So it's actually going to enter that regression equation in there for me. I need to put a stat plot. I need to turn it on. Stat plot is right above y equals. So notice these are all turned off. If I hit enter, I can now turn a plot on. It's going to put in L1 and L2. And then I will go to zoom. And I'm going to go down to zoom stat so it fits the window to the dots. Where's zoom stat? Did I skip it? Yeah, it's number 9. And what you'll see, these are the data points I entered, and if I would have entered them all, it would fit it. This is the regression line. So it doesn't go through all of the points, but it sort of averages them out. It's the best fitting line. I know that's not enough time to learn it all, but again, this is a recording we'll post back. Maybe I'll look up linear regression with the Casio. There'll probably be a good video, and I'll post one for that one as well. But this is a powerful thing because it allows us to do research, collect data, and then find a line that fits it if it is linear, and then we can use that line to make predictions. Well, what if I put more fertilizer? Oh, it should grow to this, or those kind of things, and save our farmers some time. Okay, so that's everything. Come back on Monday. We'll have our work day to get through the homework, inverse functions and linear functions.